Hey everybody, in this video we discuss recurrent neural networks or RNNs and how to implement them using TensorFlow and Keras. Up to this point, we have covered two important types of neural networks, what is known as multi-layer perceptrons and also convolutional neural networks. And both these types of networks are known as feed-forward neural networks, which means that whenever we provide an input, for example, an image, we get the corresponding output, such as the label for that input image. However, in this case, we cannot take into consideration the connection or relationship between different data points that we have. So each input-output pair will be treated independently of the other ones. However, this is a big problem when we have time series or sequential data. So for example, if you have a video data set, a video can be viewed as a bunch of images or frames that put together. And in this case, the sequential images or frames can be considered to have some kind of connection or relationship to each other. And therefore, there is a need for a different type of neural network that can take this into consideration. And that's the motivation behind recurrent neural networks or RNNs. And what's happening here is that we assume that we have a time series or sequential data. And a very important aspect here, we have this thing called a time step, right? So you can think of this as having these different input-output pairs, but now each input-output pair also has a third axis, which is the time step, right? So for example, frame 1, frame 2, frame 3, up to frame 100, if you have 100 frames in a video. And the goal, therefore, here is to maintain what we call as a state that retains information between these different time steps. And therefore, this is kind of like a visualization of what we just discussed about. When you talk about RNNs or recurrent neural networks, you have this recurrent connection or state that goes back from the output back again as one of the inputs to the network. So let's demystify this a little bit more. So what is the basic idea? So when you're working with the recurrent neural networks, so you obviously don't only have one set of features. You have one set of features for each time step, right? So at the minimum, your input has this shape or size of number of time steps. Again, let's say you have 100 time steps. And the second dimension is the number of features, right? So let's think about MNIST data set. In MNIST data set, each image is 28 by 28. And if we vectorize this, we get 28 squared or 784 features. And now if we have at each time step one different image, and let's say we have 100 of them, the size of this would be 100 by 784, right? So we added this new dimension or axis, which is the number of time steps. And in order to show or index this time step, we usually use T, right? So T stands for time. And so it means that at each time step, if I just look at, let's say, the first time step, the shape is just number of features, right? So that's kind of like the big idea here, that we are adding one dimension or axis, which is the number of time steps. And in order to understand this, one of the easiest way is to unroll this network that we have here, using this recurrent connection or state. So how do we unroll this? So you can actually consider the time step or the time axis here. And so in each time step, right, you have an input, you have an output, and also there is something called a hidden state. And this hidden state is what will be passed through the next time step. So one thing that is very important to consider here is that for these hidden states that we have here, obviously this is a neural network, so you have weights or parameters. The weights or parameters are not actually changing. We are just unrolling these through time. That's the idea behind, as I said, the unrolling through time to be able to understand recurrent neural networks. And in order to mathematically represent these, we can actually use that index T that we mentioned. So you can see that here H2 in the second time step is a function of the input at that time step, which is x2, and the hidden state from the previous time step, right? And so therefore, in general, h of t is a function of x of t and h of t minus 1, right? So if we don't have this ht minus 1, then this is exactly a multi-layer perceptron or convolutional neural network, which are both considered feed-forward neural networks. However, when we have this connection to the previous time step, that's when we have a recurrent neural networks. And then your output at each time step is a function of your hidden state, right? So these two equations here, they explain the behavior of this recurrent neural network. And the main idea here is that we have this connection or a state that goes from one time step to the other one. If you don't have these things, you can just assume that at each time that you provide an input-output pair, they will be treated independently and separately from other data points that we have. So that's kind of like the basic idea of recurrent neural network. And now let's connect this with how we can actually implement this in Keras. So the nice thing with Keras is that everything is modular. So like, for example, dense layers that you already have seen in previous lectures, you can still use. The main differences that you have here is first, if you want to just use what I just explained here, this having a state going from one time step to the next step, you can use this simple RNN layer. That's exactly the implementation of what I just mentioned. And then the other big difference here is this input shape, right? So remember, input shape right now is the size of the number of time steps. So if you have, again, 100 time steps, this should be 100, 100, and then the number of features. And then if you want to, let's say, predict one scalar for each time step, then you also put a dense layer, right, with one neuron or one unit. And if it's, let's say, classification problem, then you can use sigmoid, and then you can use your loss function, which is the binary cross entropy if you have a binary classification problem, and so on. So it's very much like what we have seen before with sequential class, except that now you can also consider this recurrent connection or states using simple RNN. But the reason that we have this here is to show you actually what this does. That's the main thing we're trying to understand here. Okay, so let's say that you have 100 time steps, as I just mentioned before, and let's say the number of input features is 10, right? So this means that right now each xn, x2, x3 is actually a vector which has 10 elements, right? Because the input at each time step is 10 dimensional. And let's simplify this, and let's say we have one of these simple RNN layers with 50 units net and one dense layer with only one unit. So this is kind of like our output. And let's use model.summary to see how many trainable parameters we have here. So you can see that we have a total of 3,101 parameters. And I want to do the math and kind of like solve this manually or by hand to show you why this is actually the case. So remember, at each time step, we have 10 units. We have this now hidden state, which has 50 units. So according to what we had before, the number of weights or connections is 50 times 10. But remember, this hidden state is actually connected to the hidden state of the next time step. So you can think of this as these 50 units to be connected to another 50 units, which is the hidden state of the next time step. And that will give you 50 times 50 weights or parameters. And as always, we also have to consider the bias terms, and that's exactly how many neurons that we have here, and that's 50 times 1. So why I didn't consider 50 times 2? Because the thing that really here you have to consider is that when I represent this using what we have here, that we have 50 units and we have 50 units here on the right side, this is not really the case. This is that unrolling through the time that I just mentioned. So we really don't have two separate, 50 neurons. It's just one, but there's this connection that goes from this hidden state to itself. And it's just easier to unroll these so you can calculate the number of parameters. So that's why I replicate these, but really in practice, this does not exist as a separate layer. So this means that just going from the input to hidden, we have 50 times 10 plus 50 plus 1. So there are 3 of these that we have to add. And so that will give you 3,050 parameters or weights total that we have to learn for this part of the network. And then when you want to go from your hidden state to the output layer, so this one is much easier, right? Because you have 50 units. And once you compute the output of this, now you have to connect everything to that 1 unit that we have at the end. And that's 50 times 1 plus 1 extra bus term for this single unit that we have here. And that will give us 50 plus 1 or 51. And if you add this, you get 3,101 units, which is very much consistent with what we see here. So that's why I really wanted to just here, the goal is not to train anything, but just to show you the fact that, you can think of these recurrent neural networks as networks that are unrolled through the time. But the only thing is that we really don't have 2 separate, layers with 50 units. It's the same, but there's this recurrent connection or state as we just mentioned here. So that's what I really always like to keep in mind. Okay, so now let's look at a little bit of like the mathematical expression behind what we said. So we're going a little bit deeper into the math behind recurrent neural networks. So as always, you have an activation function that you apply after finding the linear combination or weighted combination. And here you need to have 2 sets of weights, as you just saw in the analysis that we did. One for the input that we have at each time step. And I show that using this W matrix index HX. And then another one, which is WHH. And that's the one that goes from the hidden state to the next time step. And then we have the bus terms, right? So obviously in the case that we just had, one is 50 times 10, the other one is 50 times 50. And then we have this bus term, which is 50 times 1 or just 50. It's a vector for each single unit that we have. So you can see that overall, when you have recurrent neural networks, everything is pretty much the same, except that extra term that we have with the hidden state from the previous time step. Okay, so now one of the most important differences between recurrent neural networks and feed-forward neural networks is this idea of backpropagation. So previously we looked at backpropagation, and we showed that how you can use chain rule to be able to find partial derivatives of the loss function with respect to weights. And this is a little bit, or I would say even like more than a little bit complicated than what we had before. And this is why it is called backpropagation through time. And this is the training algorithm used for recurrent neural networks to update weights. To just give you a little bit of background on this, so the core idea is the same, right? So you have a likelihood function, and let's say this uppercase T is the total number of time steps that you have. So you want to maximize the likelihood of the outputs given the inputs and the unknown parameters of your network, right? That was kind of like the motivation behind all the networks that we have seen so far. And overall, what we can do, we can write the forward pass or how we can get from the inputs to the outputs to see how we can now go backward and find partial derivatives, right? So we have these inputs at each time, and we have this weight, which is WHX, and then WHH. And then in this case, I'm kind of like ignoring all the activation functions. You can really consider them, but it's a very easy sort of like adjustment when you're talking about partial derivatives. So that just means that you have to consider the derivative of that activation function. So that's why for now, we just ignore that for simplicity. And then once you find your hidden state, again, you have this WHO, which is what takes you from the hidden state to the output layer, and that gives you the output. And then your loss function is in the form of the empirical risk, which is the weighted average of your loss functions calculated for each data point. So this YT here is what we get from the network, and YT reference is the actual output that that we are given from our data set. So again, we want to make sure that we to understand that we made a few simplifying assumptions here, right? We omit the constant terms and the bus terms. We omitted the activation function. And the goal here is really focus on the recurrent connection, which is this part, this WHH times HT minus 1. Because other than that, this is very much similar to a standard feed-forward neural network. And the other thing that we also do to simplify this, and we have done this before too, is that whenever you have these weight matrices, you can actually flatten or vectorize them to make it simpler when you're finding partial derivatives. So now you can find partial derivative with respect to each one. And in order to do this, so for both WHX and HH, we vectorize the whole thing, and we just show that using WH, and the same thing with WHO, which takes us from the hidden state to the output layer. We vectorize that too, and therefore we get these two key equations here, that at each time step we have an input, we have a hidden state from the previous time step, and then we have this WH, and this gives us the new hidden state, and then the hidden state at time t and WO will give us the output. And so now we can start actually finding these partial derivatives, right? So let's say we want to find the partial derivative of the L with respect to WH, right? Because that's how we can use gradient descent to update this WH when we start with a random guess. Since derivative is a linear operator, we can take this inside the summation, so that part is easy. And now when we want to find the partial derivative of L with respect to WH, you can look at the equations that we have here, right? So you can find the derivative of this L with respect to YT, right? So that's what we do because this is easier since this is a function of YT. And then YT is this G function that we have, G of HT and WO. And then we find the derivative of this with respect to HT. And then finally, we go one step back in the equations that we have here. We find the derivative of HT with respect to WH. So these first two terms are easy to calculate, right? So this depends on your loss function. If it's like a mean squared error, so this is like super easy, it's a quadratic function. This one is very easy too, if it's like, let's say, just simply a sigmoid function or something of that nature. But what is really kind of like important here to discuss is how we want to find the partial derivative of this HT with respect to WH. So I'm going to go through different steps that we have here in this note that we have here. So that's kind of like where we stop in the previous sort of like notebook. And so let's find this. Okay, so what is HT? Let's write that again so we don't forget. It's a function of XT, HT minus 1, and WH. And so in order to find this partial derivative, so you can find the partial derivative of F with respect to WH, and we may be kind of like tempted to stop here. But here is a big problem that we have, that if you look at this equation here, if I use t minus 1 instead of t, then we see that h of t minus 1 depends on x of t minus 1, h of t minus 2, and wh. So this means that in this function that we have, it's not just wh that we have to consider, and actually h of t minus 1 is also a function of wh. And this comes because of the recurrent connection that we have, that now from the previous time step, also the wh, which are these parameters that are shared across different time steps. And because of that, you also have to add this extra term here, which is the partial derivative of this function f with respect to ht minus 1, and then the partial derivative of the ht minus 1 with respect to wh. And again, if you want to find this term that now I show, now you have to again take into consideration that h of t minus 1 has this h of t minus 2 here, and h of t minus 2 is also a function of wh. So this means that you have this recursive operation, you have to do backpropagation, not just through the network, but also through time. And therefore, you end up with a lot of extra terms that you have to consider, which is first, very expensive to compute, And second, you may have to deal with the vanishing gradient problem and all those cases that the gradient becomes too small or too large, right? So that's kind of like the key difference here, that because we're sharing this WH across time steps, now not only we have to go back through the network, we also have to go back through time, right? Like think about the unrolled network that we have. And the next thing is that we don't really have to be worried about this because this is already implemented in modern deep learning libraries, and that's why we use them to perform backpropagation for us. But something very important to keep in mind. And therefore, this is something that is very well known, that with the simple RNN layer, or what we just so far have discussed, we have this issue that we may not be able to remember enough from the past. And we may have to really think about how we can take into consideration long-term dependencies that we may have in our data set. And because of this, there are some modifications of these recurrent neural networks. And one of the most popular ones that I'm sure you will see if you look at different like applications and tutorials is this LSTM, or long short-term memory. And as the name suggests, with the long short-term memory, so you have a long-term memory and a short-term memory, right? So we don't have just one kind of recurrent connection. And the way that actually they call this is the long-term memory is what is known as the cell state. That runs through the entire sequence, and it allows you to add information, remove information, and even figure out how that cell state can impact your output. So in order to show this, we have this very nice representation of this here. So you can see that like before, we have a hidden state that comes to each time step and a hidden state that goes to the next time step, right? So that's exactly what we had in our unrolled network, that each time step, when you have xt and yt, we have this ht minus 1 coming to the network and hd going to the next time step. But the big difference is this cell state, right? The long-term memory that we have, and we show that using this CT. So something that is important here to consider is that we have three different types of gates with this cross notation. So this means that this is a multiplication, and each of these gates that you see are basically sigmoid activation function. Why sigmoid? Because if you remember, a sigmoid function is a function that the output is always from 0 to 1. And this is really nice, right? Because if you multiply something by 0, it means that you're going to lose everything that was inside that signal. And if you multiply by 1, it means that you don't change anything, so you let everything to pass through. So that, therefore, a sigmoid activation function can be actually viewed as a gate. And in this case, what's happening is that you have your input at time t, your hidden state from the previous time step, and based on all of these, you decide how much of what we have in the cell state we have to forget. So if this is, again, this is a sigmoid activation function, if it's close to 0, means that we have to forget almost everything we know about the cell state. And if it's 1, means that, yeah, we want to let everything through, right? So that's this part. And then we have the same idea with this input gate, right? We want to know what we have to actually add to the cell state, right? So you have all of your inputs here, you go through the input gate, and also you can have some other activation function here too, which is not just sigmoid function, just to introduce more nonlinearity, and that will be added. And this is something that goes to the next time step, right? So as you can see, the goal is that we don't want to make too many changes to this cell state because this is our long-term memory. However, before we send this to the next time step, we are able to also send this through another activation function with some output gate to decide what should be the hidden state, which here the hidden state is also the output for that time step. So you can see that we have these two lines. So the hidden state is what goes to the output and the next time step, and this is supposed to have more a short-term memory. And then for the long-term memory, we have this cell state, the line that we have in the above here, are in the top, and that's the one that is supposed to have more long-term dependencies. And this is the idea behind long short-term memory. So it seems that this is actually very much more powerful than the actual like simple RNNs or the very basic implementation that we have here. Okay, so now let's, in order to just put everything together and recap what we have, so let's look at a synthetic data set to test the performance of two different types of recurrent neural networks. The simple RNN, where we just have a hidden state, and the LSTM, where you have the solid state and hidden state. In order to create a synthetic data here, the goal is to have this structure that we just mentioned. So we want to have a time series data. So we need to have these number steps, and we put this 100. So that's the number of time steps. And then we have a different number of sequences, right? So let's say here we have 2000 sequences. Each sequence is 100 by 1, which means that this 1 here is the number of features for each time step. Okay, so that's the main format of time series data, right? So you have number of samples or number of sequences, because each sample is technically a sequence, the number of time steps, and then the number of features, which here we assume that it's 1. And since it's synthetic data, I just create this using a uniform distribution from 0 to 1. So that's the np.random.rand. And in order to create these dependencies between time steps, what I'm doing in order to create my output data, first of all, I'm going to use this cumulative sum. And what this means is that for each sequence that we have, so this I is the sequence number. So let's say you want to create your first sequence. At each time j, you're going to add all the inputs that we created up to that point, right? So that's why this k goes from 0 to j. Okay, so j, if it's, let's say, 5, that means that we want to add everything up to that time step 5. And therefore, this what means that if you want to predict the output at time, let's say j, it doesn't just depend on the input at that, also depends on all the x values up to that point, right? That's how we create that time dependency. And then in order to make this just a little bit more interesting, we are going to add some nonlinear transformation of data, which is this sine function. So your output is sine of this, for example, constant. This is kind of like our frequency times this cumulative sum calculated for different steps. And therefore, as we just mentioned, this means that each element here for j depends on all the previous elements up to j, making this a sequential data generation process. So in order to create this data, we just do what we just mentioned. We create this x using the uniform distribution from 0 to 1. And then you can use this cum-sum function for the cumulative sum. And then you apply this sine function, right? So, and we want to do this across axis 1, because if you do across axis 0, that'll be the first one, but that's not what we want to do, because for each sequence, you want to do this for the different number of inputs that we have for the time steps. So that's why we use axis equals 1. And so here we create this input-output pairs. And then we also use train test split. The nice thing is that this is very smart, knows that in general, the first axis is the number of samples. So it understands that, well, we have 2,000 data points or 2,000 sequences. And so 20% or 400 of them are for testing. And the remaining 1,600 sequences are for training. So it's important to look at the shapes of, for example, training data here. You can see that we have 1,600 by 100 by 1. So the first one is the number of sequences we have for training, the number of time steps, and for each time step, we have one input. Okay. So now in order to see how this data looks like, let's just plot 15 of these training data points that we have. So it's a 5 by 3 grid here. So you can see that in this case, we have these 100 time steps, and we have sort of like, one output for each time step, right? So we have So we have one input and also we have one output, which is easy because now we can actually visualize this. Okay, so let's start with defining our first Keras model, right? So we're going to use the sequential structure where we can stack layers. And so we're going to put this simple RNN. So this is the case that we have 10 units, and then these 10 units are connected to the 10 units that you have in the next step, right? So that's the idea behind simple RNN. And it is important to put this return sequences equals to true to make sure that actually we return one output for each time step. Since in some cases you may not need necessarily one output for each time step and you want to just produce something for your last time step, there are both options. But if you set this equal to true, you're going to have one output for each time step. And here we are going to also put one sort of a unit in our last layer. And since this is a regression problem, we're going to use the mean squared error. So then you're going to use the fit method with training data, number of epochs, batch size. I did use an validation split here because I don't want to do hyperparameter tuning. And so you can see that here we have this different number of epochs. The value of the loss function mainly goes down, which is a good thing. But if we do our predictions, now we use our test data. So the test data sequences that we have, and we're going to plot what we predict using the red color, and blue is what we have as the ground truth data. So you can see that we're not necessarily doing like horribly bad here, but you can see that we have a lot of oscillation here, but we overall, a simple RNN is able to capture the overall shape of these functions because of the fact that you can capture long-term dependencies to some degrees. But how does an LSTM network perform? So in order to do that, we're going to repeat the very same experiment, except that now we're using the LSTM layer, which is again implemented in Keras. With very similar options. I think here we also increase the number of units, but no, this is optional. You can obviously perform hyperparameter tuning to see how many units we need, and everything else the same is Adam optimization and mean squared error. And also here I increased the number of epochs a little bit too to show you the values of loss functions. Obviously we can plot the values of loss functions as the number of epochs. We have done that before if you really want to see the convergence here. But just by taking a quick look here, you can see that this is a really good model because the values of the loss function, actually, they're getting very close to zero, right? Even gets to the 10 to the negative 4. I do believe we even have 10 to the negative 5. So this means that this model, and again, we have to evaluate the performance on test data to make sure that this is not like, something like overfeeding or something like that. But it seems that we are actually up to a very good start here. And so in this case, again, we're gonna, for 15 of those testing sequences, we're gonna plot the actual values and the predictions using the LSTM model. And you can see that in this case, our LSTM model can very well predict those testing sequences that we have. So you can see that just one LSTM layer is able to capture the dependencies that we have using cumulative sum and also the sign function that we have. So this brings us into an end here. So where we have this type of recurring connection or state. So now we know that the basic connection, which is what we have in simple RNN, and also LSTM layer. I hope you found this video helpful.